In this video, we're going to start chapter 12. And chapter 12 is on kinetics. And kinetics looks at the rate of reactions. So how quickly are my products appearing? How quickly are my reactants disappearing? So how fast does it take to get from point A to point B? And then also the sequence of steps by which that mechanism or by which that reaction takes place. So we're going to look at reaction rates, and the sequence of steps by which a reaction takes place. Right? Often when you're given a chemical reaction, we have reactants generally written on the left and our products on the right, and we just show that, right? And that's usually our net reaction. Oftentimes there's going to be intermediates. So if your net reaction is, let's say, A going to B, it's very possible that A forms C first, then C forms B. And then our net reaction, right, C would cancel out, is A going to B. So oftentimes we have intermediates, which is what C is in this case. It's not just a straightforward A forming B. So we're going to look at that sequence of steps, and that's called our mechanism. We could write that up here. Our mechanism. If you go on and take organic, you're going to spend a lot of time looking at mechanisms. Here we're just going to look at it rather quickly, but again, you don't always just go from reactants to products. A lot of times there's a lot of things happening in between there. So we're going to look at some of that. Reaction rate, I had said that's how quickly my reaction occurs. Often I'm just going to say rate, but I am talking about my reaction rate. So how fast the concentration of reactant or product, we can look at it from either side, changes per unit time. Essentially how quickly or how fast a reaction occurs. And there's a large variation. You could have a reaction that's very slow, the rusting of iron, right? If you just have a piece of iron sitting out in your yard, it's going to take a while for it to rust. Or if I was to take sodium metal and react it with water, that's going to react really quickly. So some reactions are fast, some are slow. When we're studying that rate, right, when we're looking to see, is it a fast reaction, is it a slow reaction, we are looking at kinetics. I had written above that my rate is equal to the change in concentration, right, how fast the concentration of reactant or product changes over my change in time. So it's essentially a concentration change per a time change. And again, we can look at it from either the product side or the reactant side. There's going to be an increase in product concentration. These brackets, kind of a side note here, these we're going to use a lot this semester. If you see brackets around something, it actually stands for its molar concentration. So it's concentration measured in molarity, right? Remember molarity, a capital M, is equal to the number of moles that we have per liter of solution. So moles of solute per liter of solution. Be really careful to not get molarity and moles mixed up, right? Moles is the actual amount that we have. Molarity is moles per volume of solution. So be really careful. We're going to be using molarity quite a bit this semester, and we're also going to be using moles, and it's going to be really important to not get the two mixed up. So how many moles we have, this is just how much stuff do we have, right? How much of it do I have per a given amount of solution? That's my molarity. So back up to what we were writing here. I can have an increase in my product concentration. That's how we would read that. Or we can have a decrease, and actually it's not even an or, it's an and, right? As my reactants form products, products increase and reactants are going to decrease. So a decrease in reactant concentration. So we'll actually look at both of these. If I was to make a graph, and let's just say A is going to be, we'll just use this as our generic version, and I was to make a graph of my concentration versus time, my concentration of B is going to increase. I'm going to start out with none, and it's going to go up, and then my concentration of A is going to go down. Oops, didn't mean to do that. When I'm on eraser, I'm going to erase. So that concentration is going to go down. So this one would be for A, right? We're starting out up here. As time proceeds, I have less and less and less of it. And then for B, that's going to be this line. As time progresses, it increases, right? We're starting out down here without any, and then as time goes on, we get more and more and more. Also note that I'm not drawing straight lines. They're not generally linear. As time goes on, my concentration does change, so my rate is going to change. And we'll talk more about that in a little bit. I did write above, right up here, right? My rate is my change in concentration versus change in time. A more accurate way to write it, and we'll talk more about this later, is that rate is actually proportional to my number of collisions per time. It's just that the number of collisions are very difficult to measure, so we're generally going to look at amount or my concentration instead of the actual number of collisions. We're going to talk about collision theory in this chapter, and essentially what that tells us is that for two reactant molecules to react, they have to bang into each other. So if I have, the easiest way to look at it is a double replacement reaction, or even a single. If I have A and it's going to react with B bonded to C, and I'm going to form B by itself, and then A is bonded to C, what needs to happen is that A, right, it's moving around, right? We're not at absolute zero, so these guys are moving, and it has to actually come into contact with BC. So they have to kind of collide, right? They have to bang into each other. And when that happens, we're going to form the bond between A and B if that collision is energetic enough. We're going to break the bond between B and C, and then B is by itself, A is bonded to C. So the rate is actually those number of collisions. The number of collisions, though, are going to be directly proportional to the concentration, right? The more solvent molecules or solute molecules you have, it increases the odds of them colliding. So the rate is proportional to the number of collisions. We're actually going to look at concentration and know that the concentration is directly related to the number of collisions. Some other factors that affect it, so factors affecting rate. And I'm going to say rate a lot, and I mean reaction rate specifically in this chapter. Concentration, we just said that, right? If we increase the concentration, right, we have more moles in the same volume, we're going to increase those number of collisions, right? It's more crowded. They're more likely to bang into each other. So concentration, temperature. Remember, temperature is a measure of average kinetic energy, right? Kinetic energy is the energy related to motion. So essentially we can think about it at higher temperatures, the particles are moving with more energy. I had said it a minute ago, right? When A here bangs into BC, it has to be sufficiently energetic. They have to have enough energy. If they don't, they're not actually going to react. They're just going to kind of bounce off of each other. I need to form that bond between A and B, and I need to break that bond between B and C, which takes energy. So if we increase the energy, if we increase the temperature, we're increasing the energy of those collisions. So higher temperature, that's also going to increase our rate. We could look at catalysts, and we will later this chapter. Catalysts are substances that are going to increase the rate of our reaction without actually changing that reaction. So a catalyst is going to increase my rate. And then also surface area. And this really only works with solids and liquids. But if we were just think about water evaporating, if I was to have a glass of water on my desk, it is going to evaporate at room temperature. And it's going to take a while, right? The rate of that evaporation is going to be very slow. It's the rate of a physical reaction, but they have rates also. If I was to dump that water out on my desk and it spreads out, right, increasing its surface area, it's actually going to evaporate faster. So surface area is also going to affect our reaction rate. So more surface area, faster rate. Catalysts, their sole purpose, right, their whole point of being is to increase my reaction rate. Higher temperature, particles are moving with more energy. More of those collisions are going to have enough energy to react, so that increases my rate. And then increasing concentration, right, more solvent or more solute particles, right, it's more crowded, they're more likely to collide with each other. And we'll look in more detail on all of those, but for now, 4 factors that do affect the rate of our reaction. So going back to our AB example. So A is forming B. We said that our rate is our change in concentration over change in time. So using those brackets, change in A over my change in time. So my rate is going to be equal to that. Since my concentration of A is getting smaller and smaller and smaller, right? If we were to look at this, right? If I was looking at a change, I forgot my delta sign, sorry. If I'm looking at my change, remember it's always gonna be final minus initial. So I would be looking at my final molarity minus my initial molarity. Remember, A is disappearing. So every time I'm to calculate that, final is going to be a smaller number than my initial. So I would end up with a negative value for my rate, which we can't have. Rates can't be negative. You think about a car driving down the road, right? How fast it's going is a rate, right? Miles per hour. And you can't be going down the road at a negative, right, speed. So they have to be positive values. Because it would be calculated as a negative value, we do need to put a negative sign in front of it. This is kind of similar to how we did this in your thermodynamics chapter when we were talking about energy. Remember, if you had a negative sign in front of energy, it meant energy is being released. Here, you can just really think about the negative sign, meaning that it's disappearing. If we were to calculate it, we would actually have a negative value, so we need to put that negative sign in front of it to make it positive. But then also, it's disappearing. So think of that negative sign as the fact that A is disappearing, right? It's going away. Since B is appearing, I don't need to put that negative in there. So my change, that's supposed to be a delta. It's a really ugly one. It didn't get any better. Change in my concentration of B over change in time. This time it's increasing, so if I was to take my final molarity, subtract my initial molarity from it, I am going to get a positive value. So anytime you're expressing your rates in terms of a reactant, we do want that negative sign in front of it. Again, remember rates, when you calculate these, if I throw you some numbers and we have to solve for rate, it can never be a negative value. Rates always have to be positive. That negative just means that it's going away. Given an actual reaction, the relative rates do depend on the coefficients in our balanced equation, right? Not everything is 1 mole for every 1 mole, right? I had 1 mole of A going to 1 mole of B, so that was pretty straightforward. That's not always the case. So the relative rates of different reactants or products, so when I say relative, we're just comparing them to each other, depend on the coefficients in that balanced equation. So an example for us, I'm going to look at 2 hydrogen peroxide, so H2O2, going to 2 water molecules plus oxygen. And I have a coefficient of 2 in front of hydrogen peroxide, a 2 in front of water, and then a 1 in front of oxygen. Because it's not a one-to-one relationship, my rates are actually going to be different for a couple of these. So, and you can look at them from any perspective. I'm going to start with oxygen because that's the one that has the 1 in front of it. But really, you can monitor the rate in terms of hydrogen peroxide or water or oxygen. I'm just going to start with oxygen. So I would say the rate of oxygen formation, again, it's a product, so it's going to up here, is actually going to be equal to 1/2 the rate of water formation, right? Because I have to form 2 water for every 1 oxygen, it's going to take twice as long, right? So the rate of hydrogen formation is going to be half that of oxygen, right? Because I need to form 2 for every 1 oxygen. And then that's also going to be equal to 1/2 the rate of hydrogen peroxide disappearance or decomposition. You could use the word disappearance, that's perfectly fine. So because 2 of those, right, are going to disappear for every 1 oxygen, each one is going to be half the amount of time, right, because there's 2 of them. So the relative rates depend on those coefficients. If I had, let's say, 5 oxygens, it would be 1/5 oxygen is going to be equal to 1/2 water. Whatever those coefficients are going to actually end up in our denominator. And I'll write that down here in a minute. If we were to write this in terms of changes, right, using those brackets, I'm going to say that my rate is going to be equal to my change in concentration for O2 over my change in time. Remember, those delta symbols mean change for us. That's going to be equal to my change in concentration for water over my change in time. However, my rate is 1/2 that, right? And you can write it with the half if you want. More commonly, in either way, it doesn't matter, is we can put that 2 on the bottom. It's the same thing, right? And then that's going to be equal to, don't forget our negative sign this time, my change in concentration for hydrogen peroxide over my change in time, but I'm going to put that 2 down there. And again, if you prefer, that negative does need to be there, I just need to move it over. You could write it this way instead, right? It's the same thing as putting that 2 on the bottom. Either way is perfectly fine. If you're looking at practice problems from other sources, you're likely to see it both ways. What we just wrote here was called our rate expression. You do need to know that word because I could ask you on a test or quiz or homework problem to write the rate expression, and you need to know what I'm asking. So this is our rate expression. Right? Our rate expression, we can use that then to determine the rate of each substance or the rate of our reaction over a given time period. So my rate expression is essentially to compare the rate of all of the reactants and products in that reaction. A couple things that are important to note, right? Our reactants are going to have negative values in front of them. So our reactants, right, reactant concentrations disappear. So they're going to have a negative sign in front of them, right? We added a negative here. Product concentrations up here, right? They're going to increase. So positive values, if you wanted, you could go and put a plus in front of these if you wanted. You don't need to though. If there isn't a sign, it's assumed to be positive. So always a negative sign in front of your reactants. Your products are going to be positive. You don't have to write that positive there. Our coefficients go in the denominator. And then each component is actually equal to the others, right? By putting in those 1/2, by putting that coefficient in the denominator, we've now made them equivalent. So each rate is equal to each other once we take those coefficients into account. So each would actually calculate the rate of the reaction. So each component is equal to the other, provided you put those coefficients in there, right? So each calculates the rate of the reaction. So let's do one other example. So kind of a typical question that you would get from me would be to write the rate expression for the following reaction. So let's look at the decomposition of propane, or the combustion of propane. C3H8 plus oxygen. We're forming carbon dioxide plus water. And then this does need to be balanced. So I'm going to have a 3 in front of carbon dioxide. I'm going to have a 4 in front of water. And that puts a 5 in front of my oxygen. So I want you to write the rate expression for this reaction. And it would be really great if you guys would hit pause, do this on your own. After you've done it, hit play again, and then you can check your answer. Okay, hopefully you guys wrote this on your own first. And it doesn't matter the order that we put these in. If that was a question you had, the answer is it doesn't matter. I am going to start with the word rate, and then you can put reactants first, products first. You can do a reactant then a product, and then the other reactant and the product. It really doesn't matter. I'm just going to go left to right, straight across. But again, it doesn't matter. So I'm going to look at my change in concentration of propane, C3H8, over my change in time. I don't have a coefficient in front of it, so I don't have to worry about that. It is a reactant, so I do need to put a negative sign in front of it. That's going to be equal to my change in concentration of oxygen over my change in time. I do have a coefficient of 5 in front of it, so that's going to go in my denominator. Again, it's a reactant, so it gets a negative sign. Change in concentration of carbon dioxide, that's a 2 over my change in time. It's a product this time, so I don't need to put a negative sign in front of it. If I want to put a positive, that's perfectly fine. I do have a 3 as a coefficient, so that's going to go in the denominator. Let's fix that too. That was pretty ugly. And then my last one, change in concentration of water over change in time. Again, it's a product, it's appearing, so positive value. I have a coefficient of 4, so that goes in my denominator. So this would be my rate expression for this reaction. We can actually go backwards if we wanted. Let's do one more. Given the following rate expression, determine the balanced chemical equation. And again, we're given the expression, so what I'm writing is still part of the problem. So let's have a negative delta. So my change in bromide ions over 5 and my change in time, that's equal to Br2, that's a 2, over my change in time. And we have a coefficient, sorry, I have a 3 in my denominator. I'm starting to give away the answer here. Another negative bromate. Do you guys remember all of your polyatomic ions from 151? Negative, some protons, 6. And then water with a 3. So all of this is given in the problem, and we're going to actually write the balanced chemical equation. And again, if you want, I want you to want, so hopefully you want, hit pause, give this one a shot on your own, and then when you're ready, hit play again. You can check your work. Alrighty, so remember the ones with the negative in front of them are going to be on my reactant side, so they're disappearing. So this one, and this one are all going to be reactants. Remember that the number in my denominator is my coefficient. So I have 5 Br minus, that's reacting with 1 BrO3 minus, and 6 hydrogen ions. So remember, if we go back up, if it has a negative sign here, it's a reactant. My coefficients are those numbers that are in the denominator. The ones that have the positive sign are my products. So I have 3 Br2 and I have 3 water. And that would be my chemical equation. I'll do an example where we're actually going to calculate rates. So where I give us some numbers. And let's use the hydrogen peroxide example that we had earlier. So 2 hydrogen peroxide, and that's decomposing to produce 2 water plus 1 oxygen molecule. So 2 hydrogen peroxide going to 2 water plus 1 oxygen. And we're going to be given the rate of hydrogen peroxide disappearance. So if the rate of H2O2 disappearance is 0.20 molar per second, right? Change in concentration over change in time. So I'm going to have units of concentration over units of time. Do be careful. I generally write it one of 2 ways. So either, in form of a fraction, or remembering from algebra, right? If I have 1 over x, it's the same thing as x to the negative 1. So we could rewrite this as molar times seconds to the -1. And both of those forms are pretty common. They mean the exact same thing. And often I'll flip-flop between them. We could also write it, right? Moles per liter is what molarity is. So the other way we could write it is I could write it as moles per liter seconds if we wanted, right? Molarity per second. Those would mean the same thing. So this one isn't as common, but I am going to use that in this example. So I'm taking my capital M, right, my molarity, and I'm knowing that it's equal to moles per liter. So then if I want that per second, right, for my rate units, I could write it this way also. So again, just different ways to write the same unit. Just be careful not to let it confuse you because it looks a little different, but it means the same thing. And depending on what source you're using for practice, you could see it all of those different ways. So back to my question. If the rate of hydrogen peroxide disappearance is 0.20 molar per second, what is the rate of water appearance? And then let's also do what is the rate of oxygen appearance. And we can do this two different ways. They really come out to be the same way, but it's really two different ways to look at it. So the first way we can calculate it is using our rate expression that we wrote earlier, right? Our rate expression, we had a negative change in hydrogen peroxide concentration over my change in time. And then because there's two of them, I had that 2 on the bottom. I am going to write this with the 1/2. I think it's easier to think about it this way. It's going to come out to be the same. So however you like it, but I am going to put that 1/2 in front instead of putting the 2 on the bottom. And then that was going to be equal to 1/2, right? My change in water concentration over my change in time, which was equal to my change, I guess those should be parentheses, not brackets. My change in oxygen concentration over change in time. This time my coefficient was 1, so 1/1 if you wanted a fraction in front of it. So the reason I'm writing it instead of doing the 2 on the bottom, and then the reason I'm writing it with the 1/2 instead of the 2 on the bottom, is when I'm looking at the rate of hydrogen peroxide, it's only this part in the middle. This is the rate for hydrogen peroxide. This part is the rate for water, right? The 2, if I was to write it that 2 is how we relate it to each other, but the rate, the actual rate, is just this part. So for me, it's easier to wrap my head around if I actually take that 1/2 out of it, because now the things in the parentheses are actually my rate. For the first part, right, the first way to do it, I'm just going to consider these 2 parts of my expression because that's what I'm asking, right? I'm given the rate of hydrogen peroxide. I'm asking to solve for the rate of water. So the parts that I put the box around, right? This is my rate of hydrogen peroxide right here. This is my rate of water. I don't need oxygen as part of the first question, right? That's going to be my second part. So I'm then going to plug in my numbers. So 1/2. And then remember these things here in parentheses, right? This part here, that is my rate of hydrogen peroxide disappearance, which is given to me in the problem is 0.2 molar per second. And then that's going to be equal to 1/2 the rate of water. I'm just going to write an X because I'm too lazy to write delta bracket H2O bracket over delta T. So I'm just letting that equal X. You could write it all down if you wanted, but I'm just being lazy on you. And then we're going to solve for X. So mathematically, these guys cancel, and it comes out to be 0.20 molar per second. And then that's actually, we'll write the rate out this time. That's going to be equal to my rate for delta T. So we can use that expression. If we were to answer the second part of the question, I'm going to use this part, and you could use water instead if you wanted. And this part, right, we just solve for the rate for water, so we have that answer. So you could use these two instead if you wanted to. So I'm going to do the same thing. I'm going to say that this is going to be equal to x because I'm just going to be lazy on you. So 1/2 the rate of hydrogen peroxide disappearance, which is 0.20 molar per second. This time 1/1, right? So just x. So 1/2 of 0.2 is going to be 0.10 molar per second, and that's going to be equal to my rate for oxygen. So my answers here, right? My rate of water appearance, and not an eraser, my rate of oxygen appearance. So we're just using our rate expression to solve for those. The other way we can do it is just straight stoichiometry. So I have 0.20 molar per second, and that's for hydrogen peroxide. I am going to write this as moles per liter second. So 0.20 moles per liter second, and again, that's for H2O2. And then I'm just going to go up to my balanced equation. I know for every 2 moles of hydrogen peroxide, I'm going to form 2 moles of water. Because hydrogen peroxide is on the top down here, I need to put hydrogen peroxide on the bottom. So 2 moles of hydrogen peroxide for every 2 moles of water. Moles of hydrogen peroxide cancel. So 0.20 multiplied by 2 divided by 2 is equal to 0.20 moles, this time I have, of water, right? Hydrogen peroxide canceled over liter seconds, which we can then rewrite as 0.20 molar per second for water. So same answer that we got up here. If I was to do the same thing, but for oxygen, this time when I go and look at my balanced equation, it's going to be 2 hydrogen peroxide for every 1 water. That's a 1. Again, because hydrogen peroxide is on the top, hydrogen peroxide is going to go on the bottom, so they cancel. 1 mole of water, 1 mole of oxygen. Hydrogen peroxide cancels. 0.20 multiplied by 1 divided by 2 gives me 0.10 moles of hydrogen peroxide. Sorry, I keep on getting those goofed up. Moles of oxygen, hydrogen peroxide canceled per liter seconds, right? The units that are left. And rewriting that in units that look a little bit more familiar. So again, the same answer that we got up here. Either way works. I tend to do the stoichiometry method more than I do using the rate expression, but you're going to get the same answer either way. So whichever method you're more comfortable with. One more part to this problem is we can actually calculate the rate of our reaction. So be really careful here, right? This is the rate of water appearance, this is the rate of oxygen appearance. Given in the problem was the rate of hydrogen peroxide disappearance. So it's the rate specific to one of the species, right? One of the substances. So if you were to take the rate of that substance and then divide it by its coefficient, you actually get the rate of your reaction. It's basically kind of in terms of 1 instead of, 2 or 5 or whatever your coefficients happen to be. So the rate of the reaction is going to be equal to the rate of a particular substance. So one of the species in the balanced chemical equation, and it doesn't matter which one you use, divided by its coefficient. So whatever substance you pick in the numerator, use its coefficient in the denominator. So, and we could use either one. So let's look at oxygen here. The rate of my reaction, I have 0.10 molar per second. The coefficient in front of oxygen is 1, so the rate of my reaction would come out to be 0.1 molar per second. If I wanted to use water instead, water is right here, 0.20 molar per second. This time my coefficient for water, scrolling back up, that's hydrogen peroxide. My coefficient for water is a 2. Scrolling back down, divided by 2, 0.10 molar per second. It doesn't matter which one you use, the rate of our reaction is always going to come out to be the same. So the rate of my reaction, 0.10 molar per second. So do know this, right? If we want the rate of our reaction, and this is an average rate, we'll talk more about that in subsequent videos, but the rate of my reaction is going to be the rate of an individual substance in that equation divided by its coefficient.